Good afternoon, everyone. Today is lecture number 24 of this heat treatment class. And today's topic is basically TTT diagram, time, temperature, transformation diagram. We'll briefly discuss this one. This is one of the very important topic of the heat treatment as well as for phase transformation. So in the previous lecture, we have discussed something about this decomposition of austenite. We have seen a lot of things, and at the end of the yesterday lecture, in the last lecture,
So
we
today's
have
lecture
seen
25.
is 25. Okay,
Yes, sir.
25. So in the last lecture, we have discussed about that decomposition of austenite. We have briefly discussed about a lot of things, and in the end of the lecture, we have seen a diagram, right, or a plot or a graph where we have that is percentage of austenite decomposition or percentage of austenite transformation in the y-axis, and in the x-axis we have seen that is the time, right? So in that plot, the temperature was fixed, just we are changing the time, and we have to find out how much transformation has happened. That is basically, you can call it, we are checking the transformation on the basis of constant temperature. And we have seen that is a incubation period there, right? Incubation period is that period before which or up to which, basically up to which there is no transformation, or transformation will not start, or transformation will not proceed. That is the incubation period. And incubation period also justify the stability, the relative stability of austenite phase, right? Because more is the incubation period, the relative stability of austenite is more. That means it will not decompose, or it will not start decomposing, right, into other products, right? So that is there we have discussed. And also we have seen in that plot, there is a transformation start time and there is a transformation end time, or transformation start time or transformation finish time, right? That means transformation will not occur at a fixed time. It will take certain time to finish. Or you can say to 100% transformation of austenite to different product, it takes some time, right? So these points we have discussed. And finally, we got another conclusion is that if we want to know the nature and the morphology of the transformation product, then temperature is also important. We do not have to keep the temperature constant, or I mean, we have to keep the temperature constant for a particular time, but we need a plot where we can have three things. One is temperature, one is time, and one is the transformation, right? Or we can have two axes. One is for temperature axis, and other axis is for time. This time temperature, that is called time temperature transformation plot, fine, which will tell you about the nature of the transformation product. The nature means it is either tougher or stronger or harder or ductile, that kind of thing. And also it tells about the nature means whether it is the structure. It tells about the structure, like, or the morphology. Basically morphology means it tells about whether it is lamellar or it is plate shape, like that, basically. And this time temperature transformation curve is also called, this is also called IT diagram, isothermal transformation diagram, because here, if we want to plot this diagram, we need to keep the temperature constant, and we have to see at what time the transformation is getting started and at what time the transformation is getting finished, right? So we'll get lot of points, and by joining the points, we'll get lines. that is starting line or finishing line. And before that starting line, we have incubation period part. That means transformation is not proceeding or not getting started. So we'll discuss briefly about this TTT diagram, right? And recently in Vedanta, few people have got this kind of questions in interview. That what is TTT diagram and how it is helpful to determine the structures and all. Or for a metallurgy, how TTT diagram is helpful. So yes, and this diagram is also helpful to know the kinetics of austenite decomposition. Fine. Kinetics means the rate of transformation. The rate of austenitic decomposition is fast or slow. We can also determine that also by using this TTT diagram, which cannot be obtained by this iron-carbon equilibrium diagram or iron cementite metastable phase diagram. So that is the difference. If somebody will ask what is the difference between this iron cementite metastable phase diagram and TTT diagram, these are very simple things. You should simply say that in iron cementite metastable phase diagram, here we do not have any non-equilibrium products, right? We cannot able to see any non-equilibrium product. Like we cannot able to see Martensite, we cannot able to see any benite phase or benitic microstructure or Martensitic microstructure. But in TTT diagram, we can able to see these non-equilibrium products, which are very non-equilibrium products are known for their strength, right? For their hardness, for their toughness also, and for their fine grain size. And the thing is, you can understand why non-equilibrium phases are absent in the equilibrium phase diagram, because that diagram is an equilibrium diagram, which is formed due to, or we can have only equilibrium phases in the iron-carbon phase diagram or in iron cementite metastable phase diagram, because that diagram is obtained due to very slow cooling of the liquid iron or liquid steel. Is okay? Very slow cooling. If you do very slow cooling, then you will get equilibrium products or equilibrium phases. That is basically stable phases, you can say. But basically ferrite, perlite, right, cementite, those things. But in TTT diagram, we can able to see both things. We can able to see the equilibrium phases. We can able to see non-equilibrium phases. And iron-carbon phase diagram is not saying anything about the kinetics. Do not have any time axis. It is okay. In iron-carbon diagram, time axis is absent. But here in the TTT diagram, we have time axis also. At how much time the transformation is getting started, at how much time the transformation is getting finished. And it also tells about the stability also. TTT diagram also tells about the stability of austenite phase. Those things we can obtain from the TTT diagram. Then, so we'll first check this one, TTT diagram for eutectoid steel, right? So eutectoid steel is that steel which contains fully perlitic microstructure at the room temperature condition, right? Or it is having carbon weight percent of 0.8 weight percent basically, or 0.77 weight percent. So this is the, we'll see that. But before moving into that, okay, my mistake. Okay, you can see this one. This image, yes. Okay, this was done. This one, yes. So this is the TTT diagram for transformation of austenite for steel. So you can see this is the temperature axis. This is the time axis in the log scale, so that we can show small time scale and large time scale. And the temperature axis in the degree centigrade. And basically time we take in seconds to see very small changes at a small interval of time also. So you can see this line is nothing but your A1 line. A1 line is nothing but the lower critical temperature, right? So you understand this is a eutectoid steel. So eutectoid steel means above A1, austenite is the stable phase, and below A1, austenite is the unstable phase. Unstable phase means it has to transform into some other products. So above A1 we have austenite, and this is the A1 lower critical. Below this one, A1 austenite is unstable, right? So you can see this part. This part is nothing but your austenite, huh? Or you can also write unstable austenite if you want, but better to write austenite. This is austenite phase, or you can write unstable austenite. Anything you can write, that is fine. And you can see these are some temperature I have noted here. One is T1, T2, T3, T4, T5, T6, T7. Right? Suppose initially our steel is at this temperature. Now this steel is taken to a temperature of this much, T1 right now. The steel is now held at this temperature for more interval of time. So what will happen? You can see there is no transformation initially. Austenite is still there up to this, and when it reaches at this point, the austenite will start decomposing, or it will start transforming into perlite. So finally, the transformation will proceed, and at this point, the transformation will get end, or it will get finished. So after this point, you have only perlite. You can see it is written over here. So you'll get perlite. So that means the austenite has transformed into perlite. So that means in this region, in between these two lines, we have a mixture of phase. We have austenite plus perlite, right? So here, before this line, first line, which is the beginning of transformation line, this is the austenite phase, and after this line, end of the transformation, we have perlite here, right? But in between this region here, in between these two line, we have austenite plus perlite. That means the transformation has not end; it is still going on. So if you draw a line in between them, a dotted line in between them, right? So it will show you 50% transformation. So here transformation start, here in the middle it is 50% transformation has completed, and here it is 100% transformation has completed, right? So similarly, you can have many temperatures. You can see the T1 is greater than T2, greater than T3, greater than T4, greater than T5, greater than T6, greater than T7. So this is the decreasing order of the temperature, right? T1, T2, T3, like this. So at each temperature, you are holding the steel, but initial temperature is this one, and holding finally after quenching to this temperature, the holding temperature is this one. So transformation again start here like this. It is going on, right? These dot are showing the transformation start and transformation end. By joining this dot, we are getting this line, beginning of transformation and end of the transformation. Okay. Now you can see what we can. So if you look carefully this diagram, you can able to see this is a C curve actually. This is a C curve, two C curves, right? This is the first C curve, the second C curve, right? So the question may be asked like why this is having a C curve, not a parallel or not something else, right? Or some people may ask you right like this, why the incubation period is initially high, then when undercooling is done, when the temperature is getting down, the incubation period is decreasing and reach a minimum value here. Suppose at the T5 the incubation period is minimum and incubation period is maximum here at T1. Similarly, after T5 you can able to see when temperature T6, T7 again incubation period is increasing. So why? Due to this thing only, due to initially we have a high incubation period, then at the center we have a minimum incubation period, at the end we have also a high incubation period. So due to this curve is C curve, right? So for the justification, you can say like this. When the temperature of transformation is higher, that is just nearer to the A1 temperature, this one T1 for example, when the transformation temperature is higher, just below the A1 temperature, right? Then at that temperature, diffusion is the dominating mechanism. Why? Because or in other words, I can say rate of diffusion is higher, right? Because temperature is higher. The rate of diffusion is exponentially related to the temperature. If you raise the temperature a little bit, the diffusion will increase exponentially, right? So temperature and diffusion are closely related, right? If you raise the temperature, diffusion become more, or the rate of diffusion become more, right? But at this temperature, you can see the difference between A1 and this temperature is very less. So driving force availability is very less. Why? Because the temperature difference from A1 to T1 is very less. Undercooling is very less. So since undercooling is very less, so that means you can say since undercooling is very less, then nucleation is very low, right? That means the rate of diffusion is very high, but rate of nucleation is very low. So rate of nucleation is basically depending upon what? It is basically depending upon the driving force, right? And driving force basically depend upon the distance from the A1 temperature to that particular temperature, right? Or undercooling. If undercooling will be less, then driving force will be less. If driving force will be less, then what will happen? The stability of austenite is not so high. The stability of austenite is somewhat higher, not low. Our rate of nucleation is very low here. So, and overall transformation, if you look into, then overall transformation actually depends upon both rate of nucleation and rate of growth. Or in other words, you can say overall characteristics of transformation or the overall nature of the transformation basically depends upon the rate of nucleation and rate of growth, or in other words, you can say it depends upon the this undercooling as well as the transformation temperature, right? Or rate of diffusion. Fine. Similarly, if you go to a low temperature, right? If you are going to a temperature, suppose at T5 now. At T5, you can see incubation period is very less, right? Why this is happening? Because you can see the difference between A1 temperature and T5. It is very high, right? So undercooling is very high. If undercooling is very high, the austenite is becoming more unstable. So due to instability of austenite, it will try to transform easily or quickly, right? So if the undercooling will be high, then rate of nucleation will be also higher. If the rate of nucleation will be higher, then the transformation will start at a fast rate. And what happens? The diffusion is somewhat also good. Since at this point, the diffusion rate and the rate of nucleation are in optimum conditions. So the transformation start earlier, right? But if you go to a temperature below this one, T5, again, you can able to see that the incubation period is again increasing, right? It is following this trend. Why? Because at a very low temperature, this T6, T7 temperature is very low temperature, right? So the temperature is very low, undercooling is very high, driving force is very high, but the problem is what? The rate of diffusion is very low, right? Because the temperature is very low, so rate of diffusion is very low. So growth is not occurring easily, right? And as I told, overall transformation actually depends upon rate of nucleation and rate of growth, or it depends upon the extent of undercooling or extent of driving force and the diffusion, rate of diffusion, right? So that's why here in this condition, T6, T7 condition, the rate of nucleation is high, but diffusion is very slow again, right? But in the top part, the rate of diffusion is high, rate of nucleation is slow or low, right? But in this condition, in the middle portion, both are optimum, rate of diffusion and rate of growth, or sorry, the rate of growth and rate of nucleation is same. That's why it follow a C-curve way. Now we'll discuss about the effect of alloying element on TTT diagram. So what happens to the TTT diagram if you add alloying elements? And if you remember, we have classified the alloying elements into two categories. One is ferrite stabilizers and austenite stabilizers, right? So what happens to the curve? You have to remember the curve basically, apart from the cobalt, if you add other alloying elements, this nose of the C-curve, this is the nose of the C-curve, will start shifting towards the right side. This will shift to the right, this will shift to the right side. So if except cobalt, other alloying element shifts the nose of the C-curve, this part, nose part, towards right side. If it will shift towards right side, that means what is happening? That means incubation period is increasing, right? Incubation period will increase because initially incubation period was this one, but due to addition of alloying element, suppose start curve becomes this one and end curve become this one. So it becomes this one and end curve become this one. So what will happen? That means incubation period is increasing. That means the relative stability of austenite is also increasing, right? Now the question becomes why the relative stability of austenite is increasing, or in other word, you can say except cobalt, if we add other alloying element, then the rate of decomposition of austenite increases. Sorry, it decreases, not increases. The rate of decomposition of austenite increases, right? That means it will become slow. Slow means again incubation period is increasing. That means, right? It is written over here. What happens to the incubation period? So incubation period increases, or in other word, I can say the rate of transformation of austenite decreases. Then what happens to the relative stability of the austenite? It increases, right? The question is now why the relative stability of austenite increases? Because as if you remember, or in other word, you can say why. Here I can write why the rate of decomposition of austenite reduces, right? This is a same question. So decomposition of austenite will decrease. The rate of decomposition of austenite will decrease due to addition of alloying element except cobalt, because as you remember, we have two types of alloying element. One is ferrite stabilizer, one is austenite stabilizer. If we are adding austenite stabilizer like nickel, manganese, carbon, nitrogen, and cobalt, copper, these are austenite stabilizers, right? If you add these alloying elements, we understand austenite stabilizer function is to stabilize the austenite phase. It try to increase the region of the austenite, or it try to make the austenite stable even at low temperature, or it do not try, or it prevents the decomposition of austenite, in other words, right? So that part is clear. But somebody may ask why, due to addition of ferrite stabilizers also, even if apart from the cobalt, even if we are adding ferrite stabilizers, which stabilizes the ferrite phase, but not it destabilizes the austenite phase, still the rate of decomposition of austenite is decreasing. This may be a question, right? Because ferrite stabilizer means you can add silicon, manganese, silicon, chromium, right? Vanadium, niobium, titanium, tungsten, aluminium. These are ferrite stabilizers, right? If you add those alloying elements, the austenite become unstable, right? But the point is what? The rate of decomposition of austenite is decreasing. This is because maximum ferrite stabilizers are carbide forming elements. They form alloy carbides. And if you remember, alloy carbides are very stable as compared to that of the cementite, or as compared to that of the iron carbide, right? So that means solubility will take more time, obviously, or if you want a transformation, then diffusion is needed. Diffusion of carbon atom is needed. So basically, since these ferrite stabilizers form stable carbides, stable alloy carbides, so it retards the diffusion of carbon atom, right? Because in paralytic transformation, we need carbon atoms to diffuse. But if carbides will be there, alloy carbides basically will be there, it retards the, right? It hindered the, or it basically retards the diffusion of carbon, right? So diffusion carbon is retarded. It will become very slow. So obviously, then transformation will become very slow. So rate of austenite decomposition will be slow, right? This is the answer. Now the question is effect of presence of strong and weak carbide forming elements. So if we have a weak carbide, that is okay, because if we have a weak carbide, that means the carbide is not so strong, or this alloy carbide formation is not so strong, then the retardation or the effect of decomposition of austenite is what? The rate of austenite decomposition will somewhat more. But if we have a strong carbide in the steel, then there is a problem, right? Because strong carbide will not easily soluble, or the you can see retardation of diffusion of carbon is more. So the effect will be more in case of presence of strong carbide rather than weak carbide in steel. So another question, effect of alloying element for perlitic and benitic transformation. So we understand perlitic transformation is a completely diffusion based transformation. Here in this transformation, the iron atoms and substitutional atom has to diffuse as well as the carbon atom has to diffuse, right? But in case of benitic transformation, only carbon atom has to diffuse. There will be no diffusion of iron atoms or substitutional alloying elements, right? So you understand, if perlitic transformation involves diffusion of carbon and iron and other alloying elements, then the effect will be more pronounced in case of perlitic transformation as compared to that of benitic transformation, right? So rate of decomposition will be slower in this case, in case of perlitic transformation, because it retards the decomposition of carbon. Now this is a TTT diagram for eutectoid steel. Eutectoid steel means steel is having 0.88% of carbon. You can see again same temperature versus time, but temperature in degree centigrade and time axis in seconds. You can take log T. So you can see the time scales 0.1 start from 0. It is not 0.1, actually it is 0, then or otherwise point, yes, 0, then 0.1, then 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5. Your temperature is 100, 200, 300, 400, 500, 600, 700, 800, right? And this is the A1 temperature, lower critical temperature. So this is the curve. So this is the transformation start curve, and this is the transformation end curve. And the carbon percentage is very high. You can see 0.88%. And this austenite phase, and this austenite transform into perlite. It is austenite transform into perlite plus benite, and this reason austenite will transform into benite. And below this one, this line is MS. MS means it is martensite start temperature. So martensite will start forming below this temperature. So you can able to see here, this is the martensite 50% has transformed, and this line shows martensite 90% transformed. And this temperature, which is below 100 degree, we have only 100% martensite. So that means martensite start temperature and martensite end temperature in between will have mixture of phase, austenite plus martensite. And in between these two curves, we will have mixture of phase, austenite plus perlite, austenite plus benite. Now this is a curve showing a TTT diagram for hypo eutectoid steel containing below 0.88% of carbon. So you can see what is happening. The transformation start earlier. Here the transformation is delayed. Here the transformation start earlier and also finish earlier. But what we can able to see, we can able to see different phases, because you can see this dotted line is nothing but the lower critical temperature, right? We have hypoeutectoid steel. So once we are talking about hypoeutectoid steel means we are talking about two lines. One is the A3 line, and other one is the A1 line. A1 line is the lower critical temperature, where below that austenite is the unstable phase. But ferrite and cementite are the stable phase, or anyways. So, and above A3, austenite is the stable phase. So you understand, this is 800 degrees centigrade. So below 800 degrees centigrade, we will have two phase, austenite plus ferrite, right? This ferrite is nothing but the pro-eutectoid ferrite, if you remember. So the transformation, the transformation of austenite into product, any product, basically to the perlite, is somewhat different, right? In case of hypoeutectoid steel, because in case of hypoeutectoid steel, below A3 temperature, a new phase is coming out from the austenite, that is pro-eutectoid ferrite, right? So you have to remember, whenever we are talking about TTT diagram for hypoeutectoid steel, then what is happening? Below A3 temperature, a pro-eutectoid phase, that is pro-eutectoid ferrite, is coming out from the austenite, and when we are going down the temperature axis, the amount of pro-Eutectoid ferrite is decreasing, and finally, when the temperature is below A1, then or lower critical temperature, then this remain austenite will transform into perlite. So that is the thing it is written over here. You can see that means this is the lower critical temperature dotted line. So above lower critical temperature we have two phase, austenite plus ferrite, but this is the curve you can see. Now this is austenite again, this is austenite, but this austenite has transformed into ferrite plus perlite, and in between them we have austenite plus ferrite plus perlite, and this is the MS temperature. If people just carefully look at the MS temperature, you have seen the MS temperature here for for eutectoid steel, and just look at the MS temperature here for a hypoeutectoid steel, and now we'll see the TTT diagram for hypereutectoid steel. So here you understand, since we have a hypereutectoid steel, then we have two lines. One is SCM and A1 line. SCM is the upper critical temperature line, and A1 is the lower critical temperature. You can then understand this is this dotted line is showing A1 line. So you can able to see above A1 we have austenite plus cementite, obviously, because in this kind of transformation, when the steel is taken below ACM, then a pro-eutectoid phase, that is pro-eutectoid cementite, will come out from the austenite first. Then when we go to a low temperature, the amount of cementite formation will be decreased, and finally what happens when the temperature is below A1, this remain austenite will transform into perlite. So we have a two structure, perlite plus cementite. You can see this is austenite phase, this is austenite phase, this is perlite plus cementite, and this is austenite plus perlite plus cementite. And you can just see the MS temperature here. Carefully look at the MS temperature in three conditions. This is the first condition where MS temperature is here. Check the temperature, and here you can see MS temperature is here, and you can see MS temperature is here. Now the question is effect of carbon on Martensite start and finish temperature for TTT diagram, from TTT diagram. Right? Can you people tell me quickly? I want answer from you. What is happening to the MS temperature with change in type of steel, carbon steel? This is for eutectoid steel MS temperature. This is for hypoeutectoid steel MS temperature, and this is the hypereutectoid steel MS temperature. Can you people tell me, any of you want to speak about this?
Sir, with increase in carbon percentage,
Yes.
the MS temperature is going down.
Very good, very good. You have noticed it well. So can you guess what is the MS temperature here in case of approximate MS temperature in case of eutectoid steel? This one. And for this,
220 to 230.
okay, fine. I'll say 240, for example. Anyways, for hypoeutectoid steel,
340.
340 nearly. Yeah, very good. And for hypereutectoid steel, it is
190.
180 or 190. Okay, fine. Anyway, so I should write here. These are the approximate values. These are not the exact values. So for eutectoid steel, you can, okay, fine. I'll start with hypo. In hypoeutectoid steel, it was, sorry, in eutectoid steel, it was nearly 230 to 240. I'm writing MS temperature. And for hypoeutectoid steel, that means the steel is having less carbon as compared to eutectoid steel, right? So it is how much? It is nearly 330 to 340. And for hyper eutectoid steel, that is carbon percentage is very high, then here it is 180 to 190, for example, degree centigrade. So what is the conclusion? What is the conclusion? Conclusion is, similarly, if you look at the MF temperature, it is not shown over here. So if MS temperature is also decreasing, means MF temperature will also decreases. So Martensite start and finish temperature decreases with increase in carbon weight percentage. Can you people tell me, can you correlate this one with the problem we'll face in case of high carbon steel?
The MS will be very low.
No, that's fine. That's fine. But in terms of uh, the property, suppose you are doing hardening, then what kind of problem you'll face? Suppose you have a high carbon steel and you are taking the high carbon steel to the austenitizing temperature. Suppose above A3, for example. Sorry, ACM, and you are quenching it to a temperature of, suppose, 0 degree centigrade. So what will happen? What kind of problem you can face?
Sir, as the temperature is very low, so transformation may start.
Transformation may start. I'm asking about a problem. Already we have discussed that in hardening.
Sir, incomplete transformation.
Yes, incomplete transformation. Very good. So what is that incomplete transformation?
Some retained austenite may
Very
present
good.
in our
Very good.
sample.
Obviously, since I'm talking about the MS temperature, Martensite start temperature and Martensite start temperature and finish temperature. That means I am talking about, I should have martensitic structure upon quenching or upon cooling, right? I should have 100% martensite. But the problem is what? If we have a high carbon steel, then MS temperature and MF temperature is going below room temperature, right? It is going to a very low temperature, for example. It is going sometimes to a sub-zero range otherwise, or just near to the sub-zero range otherwise, right? So what will happen? Even if you are quenching the steel to the room temperature or below room temperature, still you are having some retained austenite, because martensite start temperature will be reached, but maybe martensite finish temperature will not reached, right? And this can be justified with the help of also the stability of austenite phase, because carbon is a austenite stabilizer. It try to keep the austenites in a stable phase even at very low temperature. It is okay, I think. Now this is another topic, that is TTT diagram for alloy steels. So we have talked about TTT diagram for carbon steels, and now we'll talk about TTT diagram for alloy steels. Last part. So we can have 4 types of curves or 4 types of TTT diagram for alloy steels. So you can see this is the figure 1, this is figure 2, this is figure 3, and this is figure 4. So these 4 types of TTT diagram can be obtained depending upon the conditions, whether it is low alloying steel or high alloy steels, like that, or some specific alloy steels, like that. So you can see in this curve, just look at this curve. So this TTT diagram is completely similar, or resembles, or it's completely similar to the carbon steels or plain carbon steels, right? We have austenite, we have perlite, we have austenite plus perlite. And this MS temperature, this is the lower critical temperature A1. And this TTT diagram, you can see what is happening. This TTT diagram is showing we have two bay, two bay. One bay is for perlite. This upper bay is nothing but the perlitic bay, and we have another bay that is called benitic bay. This bay is benitic bay. Bay means you understand that is a region. So this is the perlitic bay region, and this is the benitic bay region. So upper bay is the perlitic bay, lower bay is the benitic bay. And upper bay, here you can see that means austenite is transformed into perlite. In the lower bay, austenite is transformed into benite. Similarly, this is another TTT diagram. Here you can see we have only perlitic bay, right? So if we have a perlitic bay, we do not have any benitic bay. So benitic bay is absent. So in this kind of steel, benite will not form basically. That means if benitic bay is absent, benite may not form in this kind of steel, right? And for this kind of steels, the martensite start temperature also goes to sub-zero temperature nearly. So in this and last TTT diagram, you can able to see here we have only benitic bay. This one, upper bay is absent. That means perlite is absent here. So in this kind of steel, we can have, whenever we are cooling the steel from the austenitizing temperature, we can have either benite or we can form martensite, right? So these are the 4 different TTT curves for different steels. So it is explained over here. You can see figure 1. So when non-carbide forming elements are present, non-carbide forming elements means those alloying elements do not form any carbides, alloy carbides basically. So decomposition of austenite pattern is same in both alloy and carbon steel. So which is this one. So if we have this kind of TTT diagram, we can able to see that we do not have any carbide forming elements basically. If carbide forming elements are present, then austenite decompose into ferrite and alloy carbide instead of ferrite and cementite. Okay. And this TTT diagram obtained in case of low alloy steels. So this is the TTT diagram for low alloy steels when alloying content is very low. And we have basically non-carbide alloying elements. Similarly, figure 2, this one. We have 2 bays, upper bay and lower bay. It is written over here. So 2 different bays are present, one for perlite, the upper bay, and one for benite, the lower bay. This TTT diagram obtained in case of low alloy steels. So again, this TTT diagram is for low alloy steels. So you have to figure it out which alloying elements are there so that this kind of curve is obtaining, and which alloying elements are there to this kind of alloying elements are there. And figure 3, you can see this one, this figure, we have only perlitic bay, benitic bay is absent. So figure 3 here, benitic bay is absent. So benite do not form in this kind of steel. And this TTT diagram obtained in case of high alloy steels. So this kind of only perlitic bay or absent of benitic bay is formed in the high alloy steels. Especially those steels in which MS temperature shifted to sub-zero region. So here, as I told, MS temperature goes to a very low temperature, that is near to the sub-zero temperature. Figure 4. So figure 4 is this one where we have only benitic bay, perlitic bay is absent. So here perlitic bay is absent. Here in normal cooling conditions, either benite or martensite forms. As I told, in this condition, either benite will form or martensite will form upon cooling. So I'm done with this topic. If you have any questions, you can ask me.